In this video, I'm going to talk about the DI method in integration by parts. This is a very cool method, and it's going to help you to quickly evaluate complex-looking integrals. So let's get started by this example. Suppose we would like to evaluate the function x cubed e to the x. So in the DI method, I'm going to make a table. This table is going to have two columns, the derivative column and the interval column. So, and in the derivative column, we will keep differentiating. We will keep differentiating functions. And in the integral column, we will integrate functions. So here we have two functions, x cubed and e to the x. I'm going to choose x cubed to go to the derivative column because every time that I differentiate x cubed, the derivative becomes an easier function in the sense that it's going to be a polynomial of lower order. And I'm going to choose e to the x to go to the integral column because every time that I integrate e to the x, it's going to stay e to the x. So it's not getting more difficult as I integrate it, and that's fine. So x cubed goes to the derivative column, e to the x goes to the interval column, and then I will keep in the derivative column, I'm going to differentiate these functions. The derivative of x cubed, using the power rule, is 3x squared. Derivative of 3x squared is 6x. Derivative of 6x is 6. Derivative of 6 is 0. And here, going from one row to another, I'm going to integrate. Antiderivative of e to the x is e to the x. Antiderivative of e to the x again is e to the x, so this column will stay old e to the x. And you put these alternating plus or minus signs here. So starting from the first row, you start with the plus sign, and then you place these alternating plus and minus signs. Now the table is ready, and I can use this table to quickly evaluate this integral. So what I'm going to do is that I will be multiplying these diagonal functions. So I'm going to multiply these two functions together. So it's e to the x multiplied by x cubed, and it's going to have a plus sign because of this plus sign here. So that's what I'm doing here. So you multiply e to the x by x cubed, and that becomes the first function. Now you multiply minus 3x squared by e to the x. That's how I'm giving this. Next, you multiply e to the x by plus 6x. That's what I'm giving here. And then I multiply minus 6 by e to the x. That's what I'm getting here. And in the last step, you're going to multiply these functions that lie in the last row together, and that needs to be integrated. So you see, when you're multiplying the diagonal terms, you don't need to integrate them. You just simply multiply the functions. But for the last term, you multiply 0 by e to the x, and that needs to be integrated. And you see, this is an extremely easy function to integrate. 0 times e to the x becomes 0, and integral of 0 is c. And I'm done. So basically, the DI method is intrinsically it's the integration by parts method, but you're gathering all these information in a table, and it helps you to quickly do a 3-4 integration by parts without doing those integration by parts formally. So here, if you want to use integration by parts to evaluate this, you need to do 3 or 4 integration by parts. But having this table helps you to quickly write the final answer without formally doing integration by parts. Let's look at another example. So in this example, I want to evaluate the integral of the function x cubed minus 2x multiplied by sine x. And again, you know that this should go to the derivative column because as you differentiate polynomials, they are going to have to get easier and easier because every time that you differentiate a polynomial, the degree will be reduced by 1. And I'm going to place sine x in the integral column. So here I keep differentiating these functions. This is the derivative. And then you differentiate that, you get 6x. You differentiate that, you get 6. You differentiate 6, you get 0. Here, in this column, I'm going to integrate. Integral of sine is minus cosine. And then I need to integrate minus cosine. Integral of cosine is sine, and I keep the vector sign. Now, integral of minus sine is cosine. Or, another way to see that is that antiderivative of sine is minus cosine, and then the minus signs cancel, and you get cosine. And antiderivative of cosine is sine. And you see again, I stop here because I'm getting a 0. Then you place these alternating plus and minus signs, starting from the minus sign. Now the table is ready. I can use this table to quickly write down the answer to this integral. So you need to multiply the diagonal terms. So it's going to be minus cosine x times x cubed minus 2x. That's what I have here. And then you multiply these terms. Now you see that you have two minus signs. They cancel, and you get sine x multiplied by 3x squared minus 2. Then you multiply these diagonal terms. So you have plus 6x cosine x. Then I multiply these diagonal terms. That will give me minus 6 sine x. And the last two, you need to multiply these two functions that lie on the same row, and that needs to be integrated. So then that's going to be integral of 0 times sine. This becomes 0, and integral of 0 is 0. So that's the constant of integration. So you see again, I can quickly evaluate the integral without doing a formal integration by parts. And actually, if you want to do integration by parts, you need to do 3 or 4 integration by parts to evaluate this integral. Let's look at another example. In this example, I want to integrate the function e to the 2x times cosine 3x. I'm going to use the DI method. I have the derivative column. I have the integral column. I place cosine 3x here. I'm going to differentiate that function, and I'm placing e to the 2x in the integral column. Derivative of cosine is minus sine. So derivative of cosine 3x is going to be minus sine 3x. But because of the chain rule, you need to multiply by the derivative of 3x, which is 3. So derivative of cosine 3x is going to be minus 3 sine 3x. Then you differentiate it one more time. Derivative of sine is cosine. So derivative of sine 3x is going to be cosine 3x, but multiplying by a 3 because of the chain. So the derivative of minus 3 sine 3x is going to be minus 9 cosine 3x. Every time that you differentiate, you get a 3 because of the chain. And I'm going to stop here, and I will tell you why I'm stopping here. In the integral column, I start with e to the 2x, and I keep integrating. Integral of exponential function is itself So interval of e to the 2x is going to be e to the 2x, but you need to divide by coefficient of 2x, which is 2. So interval of e to the 2x is going to be 1/2 e to the 2x. I'm going to integrate this one more time. Again, the integral of e to the 2x is going to be e to the 2x divided by 2. So if you divide 1/2 by 2, you will get ln over 4. And we also place these alternating plus and minus signs. I'm stopping at this row because notice that if you just ignore these constants for a moment, the product of these two functions is just e to the 2x times cosine. And that's what we started with. So after we apply the DI method twice, so basically after constructing the first two rows, so you see that we are given that same function. And if you keep doing this, every two step, you're going to get the same function. So you will basically, you will end up inside the loop there. This will never end. So we are not going to keep doing this, and we will stop here because you're giving the same function up to a constant. And let's apply the DI method and see what we are getting. So this integral that I'm looking for, that's what I have here, is going to be equal to, I'm going to multiply these diagonal terms. So the first term is going to be 1/2 times e to the x times cosine 3x. That's what I have here. Then I multiply these two functions. And notice that you have two minus signs there. So the minus signs will cancel, and the product will give you 3/4 e to the 2x sine 3x. And the mass term is going to be the integral of the product of the last two functions in the last row. That's going to be integral of the product of those two functions, which will be minus 9/4 e to the x cosine 3x. And notice that when you multiply the diagonal terms, there is no integral sign. But when you multiply the mass terms, the last two functions, which lie in the same row, then you need to integrate it. So the DI method tells us that this integral that we are looking for is equal to this function, and then plus minus 9/4. And notice that this is the same function that we started with. So what I'm going to do is that you can bring minus 9/4 outside of the integral sign, and then bring it to the left-hand side. So you see, if you bring this to the left-hand side, it's going to be plus 9/4 times that integral. So this is what I'm getting. Now I'm going to factor this common term in both these functions. So if you factor out integral of e to the x cosine 3x, you had a 1 here, you had a 9/4 there. So you're going to have 1 plus 9/4 multiplied by this integral that we are looking for. And that's equal to this function. If you take a common denominator here, that will be equal to 4 plus 9 divided by 4, which is 13/4. And if you multiply both sides by 4/13, you can actually solve this equation for this interval that you are looking for. So this interval is equal to 4/13 multiplied by this function. And you can add the constant of integration at the end. For additional practice, you can take a look at the problems in section 6.2 of the Apex Calculus 2 textbook. And for any additional help you may need, check out mathematicians.com.